When you go out fossil collecting, you'll find quite a few interesting things if you only keep your eyes open. Sometimes, though, you find something that you've never seen before, and if it happens to be something that should fossilize really easily, that leads to quite a lot of interesting questions. Hello, all you lovely people. This might be a slightly short video today, although it never ends out that way, so we'll see how it works. But I was planning to do something else first, but then this is a bit of a sort of newsflash type thing with some interesting discussion around it. So yesterday we were out on fieldwork with a friend, just looking at a site we haven't been to for a while. It has to be done every now and then. And normally when you're working in the Ordovician, you see lots of trilobites, brachiopods and graptolites. The Ordovician around here anyway. And sponges if you're me. But usually it's these common fossils that you get all over the place in this area. Now, it's actually quite easy to get a little bit blasé about things like trilobites, because yes, I know they're cute, I know everyone likes them, but there are just so many of them. And normally what you see are fragments, and they are very, very well known. You're highly unlikely to find something new, and there are very good reasons for this. Firstly, they've got a calcite exoskeleton. So this is a biomineralized shell, which is pretty tough. Under most circumstances, it fossilizes very well. So any trilobite that's living in an environment where the sediment is building up has actually a pretty good chance of ending up in the fossil record. And then you've got the additional multiplication of the fossil record of each trilobite because they molt. They can molt, depending on the size of them, maybe up to 20 times in their lifespan, which means that each trilobite is producing 20 exoskeletons. And each exoskeleton consists of, well, you've got the cranidium, you've got the three cheeks, you've got the hyperstome, you've got all the thoracic ribs, you've got the pygidium. Yeah, there might be a dozen or so pieces there. So you've got one trilobite, which, if it molts 20 times and disarticulates completely, leaves 200 fossils behind. They tend to be quite overrepresented in the fossil record. And if you're looking at the ecology, this is something you really have to bear in mind, because a brachiopod only produces 2 shells in its whole life. If a trilobite produces 200, there should be 100 times as many trilobites as brachiopods if they were equally abundant in life. So this is something you really have to be careful of. So that's one thing. 2 things. The other thing is that they're very, very popular, and that they tend to be the sort of thing where a nice fossil does get picked up. A nice brachiopod or nautiloid probably doesn't, quite often, sadly. A nice sponge, people don't even notice. But trilobites do get noticed. They do get collected, they do find their way to museums, and so you end up with them being studied, monographed, and this has been going on a long time. In fact, this area where we live, the Biltlandrin-Inlier, is one of the sites where the first ever described trilobites came from. The main one was now known as Ogagicavella debucki, which is, it was described by Edward Llwyd in 1698, along with Trinucleum fimbriatum, which is just the head of a little trinucleid trilobite, which is now Trinucleus fimbriatus. And these were both described for the first time, 1698, 1699, and then at that time, they didn't really even understand what fossils were. They were described as figured stones, and the one was a flatfish and the other was 3 nuts. There you go. But that was the first description of trilobites, and people have been coming back for the 300 years since. It's been monographed, it's been studied in minute detail. People like Peter Sheldon have done this trilobite microevolution work. It's one of those areas where everything has been done, you would think. And therefore the odds of finding something new, even for the Biltlandrin-Inlier, just for this small area, are extremely slim. You would think. However, it's a little more complex than that. So when you do find something new, and it does happen, things get rather interesting quite quickly. And if you spend enough time, chucking trilobite bits away because there's only so big a house you've got, then you do get a search image of anything that isn't what you're expecting, anything different. And this does happen. So, for example, there was Medotonella serrata, which is a spectacular odontopleurid trilobite that was abundant in one stream section through 60 metres of mudstone, and it never turned up anywhere else, apart from a single fragment of a thoracic rib. Luckily, it's quite distinctive ornament from Castlebank, and a single complete articulated or semi-articulated molt from another site about a mile away. All of the ones in the type locality, this long stream section, there were loads of fragments, were fragmentary. No complete specimens there. The most complete specimen is a single one from another site, where there's not even been a fragment found. I do not understand the ecology of this thing. I don't understand what constrains its distribution. It's just something we feel that we really need to get our heads around, but we don't know what the answer is yet. But when you do find a new trilobite for the area, it's almost certainly, of course, going to be a fragment, because most fossils of trilobites are, because the skeletons disarticulate after they die. If they molt and get washed around, they disarticulate. We're lucky here in having quite a large number of complete trilobites turning up, but in general, the majority of any species is going to be found as fragments. So you find a new species, it's going to be a fragment. Like this one that turned up yesterday. Yeah, that's not a fragment. I have to give credit to Lucy for this one, unfortunately. She knew exactly what it was when she saw it, and it split on this tiny piece perfectly around the fossil, which is always rather nice, and also extremely unlikely. And it was a bit of a surprise, and we still don't know what it is to species level. We do know to family, though, it's a cyclopid. This is a very well-known family of trilobites because they're just amazing things. And you can see immediately that it's got a very sort of rounded, streamlined sort of shape. It's quite different to most of the things you see. It looks hydrodynamic. And the other thing you might notice straight away is that it's got enormous eyes. They take up virtually the entire side of the head, the cephalon, because the stomach's in the middle here. And it's got hundreds, if not thousands, of lenses on each of these eyes. And this is, well, the whole thing, but this gigantic eye is also predominantly a feature of things called the cyclopid eye. These are interesting trilobites. They are thought to be mesopelagic. So this is not living on the seafloor, but in the water column, but at depth in the water column. They only turn up in relatively deep water environments. So if you go out into the ocean basins, where you have deep water mudstones being deposited, you get into an assemblage where the cyclopids can actually dominate the trilobite faunas, and any benthic ones are likely to be blind, so eyeless ones, because when it gets deep enough, there's just no light down there. There has been work that's been done on these, looking at analysing the optics of the lenses and the interlens angle and so on. And you can work out an eye parameter, which is quite a well-known technique that's been applied across a lot of modern marine arthropods, to establish what sort of light levels these trilobites were adapted to. And for these cyclopids, the answer seems to be quite low light levels. So they're normally estimated around 180, 200 meters, that sort of water depth, which is around the depth of the shelf edge in the modern world, where it drops down into the abyssal plain and the slope. And this would be at the limit of useful sunlight. So the most tolerant of plants the sort of crustose algae that can survive on very low light levels can just about manage to work out a living about 150 meters or so in clear water. So it's that sort of level, ones where there's barely any light, but just enough to see by if your eyes are big enough. So it's a cyclopygid. Straight away we know that. And we can look at the features of it and compare it with a basically monographic treatment, a paper describing all of the cyclopygids known up until 2002 from the bill thin layer. And there are quite a lot of rare species. And there are quite a lot of, there are 2 or 3 species that are relatively common. And we can say straight away that it's none of them. So there's a thing called Degamella watersoni, which is the most common one, and in that case the eye is only about half the length of the cephalon. So clearly not that. There's a thing called Tricyclopygi binodosa, which has a couple of nodes on this segment here. It's not that. There is one that looks very similar superficially, called Sagavia, possibly novacaliformis. It's from Kazakhstan originally, but a single partial specimen has been described from this inlier, and that is different because the eyes are parallel. The inner margin of the eyes are parallel to each other, and here they're clearly oriented inwards towards the front. So it is not one of the normal suspects. There's a crushed partial specimen, just a cephalon of a thing called, Microparia brachycephala. And that might be vaguely similar, but I've seen images of complete specimens from the Czech Republic, and again, it doesn't seem to match that well either. So pretty certain now that it is not one of the ones that has been described already. There are some very interesting features here, and one thing I've been looking at, on the thoracic segments, either side of the axial ring, there's a little tiny hole on the back margin on each side. And this is the internal mould, so that would actually be a little bit of spike or peg sticking down, and presumably that's something that muscles were attached to. But it's a fairly distinct looking feature. Now, quite a few of these species that have been described seem to have something similar, but not as well developed maybe, but that's going by images which haven't been highlighting it. So it's difficult to make out exactly what this is. I am no expert on cyclopygids, and what I need here is, an expert on cyclopygids. But for the moment, I can say that I'm pretty certain it's not one that has been described for the bill thin layer before. It's not one I've seen before, and it may be a new species or it may not. But it's rather a lovely specimen. And it's the prepping is a little bit rough so far, so that can be tidied up a bit. But basically, the margin of the front of the head seems to be here. And that is the margin of the eyes, which has come out rather nicely. So it's not been damaged, it's just not quite fully prepped. But the detail is there. So why would a cyclopygid be so rare? Because it's not the only one. We've had other trilobites from this site, in fact, which are the only record of a species or a genus even in the inlier. One of them is a partial specimen of a thing called Bohemilla, which has this great big long spine sticking out the side of its cephalon, which is rather lovely. Never seen that before, neither has anyone else in this entire inlier, which, remember, has been studied for 300 years, and not just by trilobite experts, but by graptolithologists, brachypodologists, spongiologists. All sorts of specialists have come to this area and spent a long time working here. And this has never turned up before. So, why would that be? Why would we have multiple species of cyclopygids which have very, very low abundance? Now, for cyclopygids, there is actually a potential explanation. The water depth in the bill thin layer never really got much deeper than that threshold of about 180 to 200 meters in our interpretation. There's one or two sites in the time when the water was deepest, where you get them moderately commonly, but they are never abundant. They're never the most abundant trilobites. But if you go out to the very deep water environments down in southwest Wales, you can get places where the athaloptic assemblage, as it's called, including these cyclopigids, are the dominant trilobites. So we're not in that level of water depth, which means we're just in the sort of getting into the range where cyclopigids can thrive. So you will get the odd one you would expect, just straying out of its normal range and turning up as singletons here and there in areas where there is no established population. It probably wasn't actually living and reproducing here, one could say. It was just a poor lost individual that never made it home again. And that's quite likely. For cyclopigids, it makes sense. But for this site, there's a bit more to it than that, because there are also other trilobites that we have found here over the years, and we've been quite a lot of times over the years, because there's other things here as well, like stylophthon echinoderms and sponges and palaeoscolecids. And so we've spent a bit of time here, and we have had multiple species, probably 3 or 4 species of trilobites that are otherwise unknown from the built-in layer, and they are usually a single specimen. How does that happen? We're not looking here at things that look like they're out of their normal range. I mean, I guess it's just possible that all of them were lost ones that just turned up in the area, but it doesn't seem likely. And this is leading on to a much bigger question, because you have here a species of organism that can multiply its bits of fossil material by a factor of at least 100 times. Again, you consider the number of pieces and the number of molts. It should be obvious in the fossil record. It's in an environment where they're being preserved really well. So how rare was it in life? If it was 1/100th as rare as we see it, then that is pretty rare. But that assumes that we have a fossil record that we can take at face value, that what we see is a good representation of what was alive. Is that true? There's a couple of questions here. Firstly, there's the issue of actual rarity versus fossil rarity. And then there's the issue of how likely any individual trilobite is to be fossilized. Now, the latter is actually quite hard to assess. It's often said that, there's a tiny, tiny chance of any individual being fossilized, but that might be taken over the entire population, over its entire range and different environments and so on. In an environment where calcite skeletons are clearly being preserved, it's much higher chance, because obviously the sedimentation regime here was good enough that it was suitable for things being buried gradually or quite abruptly. There may be breakage of the skeleton by scavengers and so on, but we're seeing small pieces of trilobites. We're seeing broken ones. So maybe most of what was living on the seafloor and had a calcite skeleton here is actually being fossilized. If there was dissolution going on en masse below the surface after the sediment's been deposited, then we'd expect to see lots of barren intervals where you just don't get any trilobites. And maybe we see a few in these beds, but mostly we don't. Mostly we see trilobites, which is interesting. So that suggests that in this particular location, pretty much everything that was living there was being fossilized, if it had a calcite skeleton. So we come to the other question. How rare is rare? And this is where it starts getting much more interesting, and where people, I think, overlook an obvious problem that you don't overlook if you study entomology, for example, or modern marine biology. So a rare species today in the modern world, if you're into biological recording, is not something that you'll only find 1 or 2 of in any site that you go out to visit. It's not something that you'll only find 1 or 2 of per year. It's something that you'll probably never see in your lifetime. because they may have very low population densities. So if you scour a square kilometre, there might just not be any in that square kilometre to find. Or it might be one which is highly localized, has extremely specific requirements, something about the environment that it needs, and anywhere which doesn't have that, it's not there. So there are, well, for example, there's the Cornish shield bug today in the UK, which lives only on one cove in Cornwall. There's an old record from a place in South Wales as well, but that's it. The whole of the UK coastline is available to it, and it doesn't live anywhere else. There are lots of species with very, very limited distributions, which are extremely rare. There are lots of rare species that also undergo some sort of dispersal phase. So they live in one environment, and at some point in their life cycle, you get a few adventurous individuals wandering off and trying to find somewhere new to colonize. And this is how things colonize in general. There's many, many species do something like this. Sometimes that is in the marine species, that's the larval phase. So they produce larvae which float around in the sea, get transported somewhere else, settle, and then turn into the adults. And so you do have a chance of something turning up all over the place. But if you go looking around rock pools seriously, you'll find many of the same species again and again and again and again and again and again. And every now and then you will find something that is new to you. And you'll look it up feverishly in the books and hoping to find something that's never been seen in this coast before. And you find that it's still classed as occasional or uncommon perhaps, but it's not a rare one. And that is normally how it works. The rare species are genuinely rare. Even if a habitat or a locality is within their range, you're not going to find it there. There won't be any there to find. Now compare that with a fossil site. In this area, we've got quite a lot of loose blocks, actually. It's one where there's no actual outcrop, but we have a lot of loose blocks from a landslip, probably. And in those blocks, you find many of the most common species every single time you go. There are other things which are scarcer, which you will find every now and then. And then there are ones which you might find one of in your entire career of collecting there. And then there are things which one person will find one of. And if you think about the distribution pattern of biodiversity through an ecosystem, what we've called the hollow curve before, looks like this, then that is exactly what you would expect, because there are a few common species that dominate the ecosystem, common and ubiquitous. There are some rarer ones which are still quite frequent. And then there is this long, long tail of really quite rare species, which may occur in ecological samples, when you can sample everything that's in an area quite thoroughly. They may occur there only as ones and twos. When you're looking at a fossil deposit, you're not going to see everything that is in even a block of stone, because you're splitting it. You're not splitting it along every possible fossil, because rocks don't break like that. If you could dissolve the rock and get all the fossils out, then you could see where everything that was in a single block, but mudstones don't work like that. Not with calcite fossils, anyway. So it's another reason why we have to be very circumspect about what we mean by rare. When we see something that is uncommon as a fossil, it could well be that it was actually quite abundant. And in terms of what we would call quite abundant in terms of biological recording, but we just don't have enough of a fossil record because we don't have the rock exposed absolutely everywhere with the fossils all laid out for us to collect. We don't have enough of a fossil record to see them. And it's something that's easily forgotten because we can be really thorough with a fossil site and we're still only scratching the tip of the iceberg. We can get a lot of diversity, but it's never going to be the total diversity because all of those rare things are unlikely to turn up anywhere you look. That's a bit depressing, isn't it? Except it's not really, because it means that anytime you think you've exhausted a site, that you've collected everything there is to find, you're wrong. There will be something else that was living in very low population density, or that was living in an adjacent area and another one passed through. You can get slightly bored finding the same things again and again and again, but it's the rare things that will quite often tell us something unexpected. Speaking of which, let's have another look at this, because the eyes are rather remarkable. One thing you notice when you look at this is that it's got these gorgeous eyes. They are what we call holochroal eyes. They're compound with many, many lenses all abutting each other. They're simple lenses. It's a bit like the eye of a dragonfly today. Hundreds, if not thousands, of lenses, each of which was creating a point of light, effectively, and the image was generated as a mosaic of all those points of light. So it's not as sophisticated as some trilobite eyes. The schizophrol ones are ridiculously complex, but it's still, it's going to be generating quite an interesting image, and there'll be quite a lot of resolution here. But there's some interesting detail here that I noticed when looking at it, which is probably quite common in cyclopigids, but I've never seen it documented before, but I don't know the literature, so it's probably out there. I'll have to go looking. But the lenses are not all the same size. These ones on the top of the cephalon are about twice the diameter of the ones going round the side and towards the underside. The lenses get smaller towards the bottom of the trilobite. Now, isn't that interesting? Because the larger the lens, the more light it can gather, and the better adapted it is to low light conditions. The more numerous the lenses you have, the better an image you can create. So if this is swimming in this orientation, and you have eyes in which the lenses on top are adapted to low light when it's looking up towards the area where there is more light, but the ones on the sides and looking downwards are adapted to having more light but better definition images, that's not what you'd expect. And the first thing that crossed my mind was a slightly balmy idea that this is actually evidence that there's bioluminescence, that these things are swimming around in the pelagic zone or the twilight zone, and they were able to see things below and to the side of them that were generating their own light, and those eyes around the side were adapted to looking for objects which actually were creating their own light, and that's what either its food sources or predators that it had to avoid. Whereas the ones looking up, it just needed to know whether there were sort of shadows going across it, and it can cope with that being slightly vaguer because it's got more light up there anyway. Unfortunately, this lovely idea was completely scuppered by a very obvious second thought that came a little while later, which was that they swam upside down. And it turns out that this is widely accepted, that cyclopigids are thought to have swum upside down. And as far as I know, there's no direct evidence for this has been quoted. It's just that by comparison with a lot of modern arthropods of this sort of nature, and these pelagic sort of swimming arthropods, most of those swim upside down. So probably cyclopigids did too, because it was a good way of swimming around. And yeah, I think this might actually be evidence supporting that, because the lenses should otherwise be the other way around. They should be smaller on the top and larger at the sides. So, yeah, I'm not totally sure exactly whether this constitutes good evidence or whether someone's seen this before and that's part of the argument. So going to have to go into the literature for it. But this is just playing with ideas, really, and seeing what you can get out of fossils just by spending a bit of time looking at them and seeing where the ideas take you. It's a question of observation, inference, deduction, kind of. And yeah, and this is, again, the beauty of paleontology. You don't have to have a big lab to establish something potentially new. You just need to think in the right way, find things, and then interrogate them, see what they can tell us. And usually, any fossil you find can tell you something interesting if you just think of the right questions to ask. Anyway, I think that will do it for now. It wasn't too long. Actually, it was quite long. Oh well, never mind. Going to be slightly intermittent over the next couple of weeks as various things going on, but hopefully I'll have a couple of different things for you that have been requested in the past as well. So yeah, I will see you again sometime soon. Bye for now, and thank you for listening.